Welcome to lecture 9, which is on source transformation. So today we'll be seeing how we can transfer one type of source into other one to simplify different types of circuit and do some circuit analysis. Before doing that, let's revisit some of the circuits discussed so far, especially the ideal voltage circuit and the ideal current circuit source. So the ideal voltage source under load. So ideal voltage source under load can be drawn as something like this, where this is voltage source with Vs and the current flowing is I, which is given by I is equals to Vs by Rs. Okay, so let's say if this RL load resistor was shorted. Okay, in that case we have shorted RL, which means RL is 0, right? And so in case of short, that implies, so substituting this RL into this equation, that implies I tends to infinite, and any ideal voltage source cannot actually supply infinite current. So this is the limitation of ideal voltage source. And to fix this, what we can do is we can add a resistance, and the resistance cannot be parallel because then equivalent resistance will again be 0 if we have a short circuit, right? So we add a resistance in series, and that makes the practical voltage source. Practical voltage source, which is written as like this. This is the source resistor related to the voltage source, and this is Vs, and so this is the practical voltage source. And similar to the limitation of ideal voltage source under load, there is also limitation of ideal current source. So let's see that. Ideal current source under load. Okay, so let's say we have this ideal current source, which is given as this. Is the current generated, REL is the load resistor, and let's say the voltage across the load is V, and then V can be written as the product of current and the resistance, right? And let's say the circuit was open, right? In open circuit case, we have RL tends to infinite, right? Because open circuit is basically the circuit is open to air which has infinite resistance, and that leads us to getting a value of voltage of infinite, right? And in practice we can never have a situation which the current source produce infinite voltage. So the simple fix around this is again having an internal resistance, but earlier case we had internal resistance in series, right? Since RL is already infinite, there is no advantage of including resistance in series. So in this case we are going to include resistance in parallel. So that makes the practical current source, which is written as this. You have a current source Is, and you have a resistance source resistance Rs in parallel to the current source. And let's see the relationship between the practical current and practical voltage source. Okay, so let's do this parallelly. Practical voltage source under load, and in the right we have practical current source under load. Okay, so practical voltage source is basically series resistor and a voltage source with Vs, right? And under load we have extra load, which is RL, and this is plus and this is minus. And the voltage across RL, right, can be denoted as VL, which can be calculated using our knowledge of voltage divider rule, which is basically Vs times resistance under consideration divided by equivalent resistance, which is the sum in case of series, right? So let's say this is equation 1. Now in case of practical current source, this will look something like this. And this makes the RS and IS makes the practical current source, and then we have the load RL, and let's say the current flowing through this load the load is IL, and the voltage across this is again VL. Okay, now using the current divider rule, we can calculate the current across the load, right? And which is given by IL is equals to IS times 1 by RL divided by 1 by RS plus 1 by RL, right? And this gives us IS RS divided by RS plus RL, right? So now comparing these two equations, let's say this is equation 2. Okay, what we can do is from equation 2 we can calculate the VL in case of ideal and in case of practical current source under load, right? That is IL times RL. Substituting this from equation 2, we get IS into RS into RL divided by RS plus RL. Okay, so this is per practical voltage source, this is per practical current source. Okay, now if you look into these sources, if they have the same resistance and if they are trying to generate same voltage, there should be equivalent circuits, right? In this case, Vs should be equal to the product of Is times Rs, right? So two voltage source, are equivalent if they produce same voltage. Okay, that leads us to the topic of the discussion today, which is a method of source transformation. So if we have a practical voltage source, given by voltage Vs and Rs, then it is equivalent to a practical current source with current Is and a resistor Rs in parallel. In both cases the Rs are same if Vs is equals to Is times Rs. So this symbol, which looks like this actually, instead of that. Okay, so this means given one form of the circuit, we can transform into other one and vice versa. So they are equivalent circuits, and this can be really useful to simplify circuits. because the repeated conversions between these two forms may actually result in an effective way to simplify the circuits. So what we can do is, once we do some sort of transformation, we can add the series voltage source and parallel current source. So let me write this down. Repeated conversions between the two forms may result in an effective way to simplify circuit. Okay, it may actually result in simplifying circuit, but sometimes this might lead to a dead end, and it makes just the problem complicated. But with practice, this conversion from one form to other form is a really effective way to simplify circuits. So to do that, what we can do is we can have series voltage sources add up. So series voltage sources may be added, right, based on Kirchhoff's voltage law, right? And parallel current source may be added. That is from Kirchhoff's current law. Okay, let's see this with an example. Two ampere current source. We have a resistance in parallel which is 6 ohms. We have another resistor which is 6 ohms. We have this resistor which is 5 ohms, and we have this resistor 1.5 ohms. We also have a resistor here with a voltage source, negative, and this side is positive. So 34 volts is the magnitude of voltage, and this resistor is given as 17 ohm. And we also have a current source here which is given as 1 ampere. Okay, and we are required to find the I0 using the combination of different source transformation. Okay, so the question is, use series of source transformation to find I0. Okay, now looking into this, we have practical voltage source and practical current source, right? So we can actually reduce that. Let me use a different ink. So from here to here, so this side of the circuit, we have practical current source. Similarly, we have practical current source here, and we have a practical voltage source here, right? Let's say this is A dash, B dash, C dash. Okay, in that case, in this question, we have A dash is our practical voltage source, right? Practical voltage source, and BB dash can behave as a practical current source, and CC dash can behave as practical current source again. So if we do like transformation, repeated transformation between these, we can get we can solve the problem. So let's try to convert this current source into voltage source first. Okay, so okay, so this was the 6 ohm resistor from this example. So I'm converting this into a voltage source, a resistor, and a current. So this resistance will be same as this resistance, which is 6 ohm, because the equivalent circuits will have same resistance, and the voltage Vs is Is times Rs, so 2 times 6, so this will be 12 volt, and the direction is based on the magnitude, the direction of the currents. So current leaving the terminal is positive, so it's going up, so this is positive, this is negative. Similarly, this resistor Rs for the current source will be the same for the voltage source, which is 5 ohm. This voltage is then product of this and this, Is times Rs. 1 times 5 is 5 volts, and I should not have done this polarity, but I already did it. So the current is exiting from this side, so this side will be positive, and we have this part remaining to draw. So I naught, this is the 1.5 ohm, and we still have this resistor and this voltage source here, which is 17 ohm and 34 volts, right? So 34 volts. So looking into the circuit, at least this part of the circuit, right? This part of the circuit, we have the voltage source and the resistors in series, and we just wrote it down that the series voltage may be added using KVL, right? So to simplify this this circuit further, we can add up the resistors and we can add up the voltages. Okay, so doing that, okay, back to the original pen. So doing that, we'll have one resistor here, which is the sum of these three, 6 plus 6 plus 5, which is 12 plus 5 is 17 ohms, and then we'll have only one voltage source, which is basically going from negative to positive and then negative to positive, so they are in series, same polarity, so that will add up. 12 volt plus 5 volt is 17 volt, and we have the rest of the circuit as it is. So we have 17 ohm, this one is 17 ohm, and we have the voltage source, right, 34 volts, and we have the 1.5 ohm, and this is the current we want to determine. So now we have two voltage source. In our area, our current of interest is in parallel. We can actually convert these voltage source into current source and finally find I naught. Okay, so to do this, let's convert this first part, this one here. So this one can be written as a current source and a series parallel resistor. Similarly, this source here, that can be written as a parallel resistor and a current source, and finally our leftover part of the circuit, which is 1.5 ohm, and this is I naught. Okay, since this is 17 ohm, this resistance will be 17 ohm. Similarly, since this is 70 ohm, this will be 17 ohm. Now the current is going goes from negative to positive side, right? So the direction will be like this, and it again goes from negative to positive. So in this case the direction will look like this, and the current is Vs divided by Rs, 17 volts divided by 17 ohm, it's equals to 1 ampere, and in this case it will be 34 volt by 17 ohm, which is 2 amperes. Okay, so that should be all. Now what we can do, so we have two resistors in parallel and two current source in parallel. So the parallel source add up, right? So if I have to reduce these to single source, and this will be 1.5 ohm, which is we still need to decide that. Okay, so what we can do is these two resistors, they are in parallel. So 17 parallel 17 is basically 17 divided by 2, which is 8.5 ohm, and this one is 1 ampere going up, the other one is 2 ampere going down. So the resulting current will be 2 minus 1 going down, which is 1 ampere going down. And now at this point, what we can do is we can use current division rule, right? So if we apply current division, we can easily calculate I naught, which is source current, which is 1 ampere, times 1 divided by 1.5 divided by 1 divided by 1.5 plus 1 divided by 8.5. And if we calculate that, that is 0.85. However, the current division or the voltage division rules, they don't keep track of the sign of the current, so unfortunately we'll have to look out for those. So looking into this circuit, the current is flowing down, but we have assigned the current as flowing up, right? So basically I naught has to be corrected in terms of sign, so that will be negative current. That's all. I hope you understand this example. Let's see one more example and make it clear. Okay, so another example. Okay, we have two voltage source, one current source. This is 6 ohm, this is 1.6 ohm, this is 8 ohm. Voltage across 8 ohm is something what are going to determine. This is given as 36 amperes, this is given as 60 volts, this is given as 5 ohm, this is given as 20 ohm, this is given as 120 volts. Okay, so you might already realize what are the transformation that we can potentially do, right? So this section here, voltage in a resistor in parallel, in series, so that is something we can look into for transformation into current. There is another part where the voltage and resistor are in series, so maybe we can do transformation of this part, and then we have from here to here and here, so that is basically, let's say, C transpose. Okay, so that's where we have a current source in parallel with the resistor, which is a practical current source. So the question asked is find the value of voltage B. Use source transformation to find voltage V. Okay, So what we can do is we can first convert the voltage source to current source, because if we do that we'll have 3 currents in parallel and 3 resistors in parallel. So we can simplify that and use the voltage division rule to calculate the voltage across 8 ohm resistor. Okay, so let's do that. So this will result in a circuit that looks like this. And let's say 1.6 ohm, 8 ohm, plus minus V, we have 6 ohm. That is something we want to calculate. We have 36 amperes, right? That is given. So converting this circuit into a current source and a resistor look something like that, and converting this a dash into current source or the resistor will look like something like that. So the first part, we have the resistor is given as 20 ohms, so this will remain same, right, between voltage and current. The second part, we have 5 ohm, that will again remain same, and we can calculate current as the voltage divided by the resistor. Vs is equals to Is times Rs, right? So we can calculate Is as Vs by Rs. So in this first case, the current is 120 volts divided by 20 ohm, which is 6 amperes, right? And in the second case here, we have 60 volts divided by 5, which is 12 amperes. Okay, now we see that the polarity positive sign is in the upper direction, so the current flowing in this case is up. In this B to B dash case, the positive terminal is on the lower side, so the current is down. Now we can see that this part of the circuit, so this one highlighted here, we have currents and resistors in parallel, and we know that we can actually add up, right? Add up and find equivalent current or the resistor in this case. So that will reduce us to the resulting current, which is basically sum of all. So let's assume the opposite up direction as positive, so 6 ampere minus this one is negative 12 ampere, this one is again positive plus 36 ampere. That will give us 30 ampere, and that is in the upward direction. Okay, and the resulting resistance, right, is basically parallel combination of this 12 ohm, this 5 ohm, and this 6 ohm. 12 parallel 5 parallel 6, right, which is 1 divided by 20 plus 1 divided by 5 plus 1 divided by 6, which will give us 2.4 ohm. Okay, now we can use this information and redraw the circuit again. So this is the second part of the circuit with 8 ohm resistor here, 1.6 ohm resistor here, and the voltage of interest is this volt, right? So now we have calculated the R equivalent is 2.4 ohm, and our equivalent current is 30 ampere going up. Okay, so finally, if we can transform this part of the circuit, which is which is a practical current source, into voltage source, then we have one voltage source, one series resistor, and other 2 series resistor, then we can use voltage divider rule to find the voltage across the 8 ohm resistor. Let's do that. Let's convert this into a practical voltage source. Okay, so this is 8 ohm, this is volt 6 volt, So converting from ideal current practical current source to practical voltage source, the resistance remains same, right? And the voltage is given by the multiplication of the current and the voltage, current and the resistor. So 30 amperes times 2.4 ohms, which will be 72 volts, and the direction is the positive terminals where the current is leaving and negative in the other side. So right now we have simplified the circuit, and using the voltage divider rule, we can calculate the voltage across 8 ohm, right? So voltage across 8 ohm is given as using the voltage divider rule, right, which is the source voltage times the resistor of interest, which is 8 ohm in this case, divided by the equivalent resistance, which is the sum of these three series resistance plus 1.6 plus 8, and that will give us a value of 72 times 8 divided by 12, which is 48 volt. So this way we can solve this circuit, this type of circuit using a series of source transformation. So we have discussed that the parallel currents and series voltage can be combined, right? How about combining parallel voltages? Parallel voltage, they cannot be combined because it violates the Kirchhoff's voltage law. We discussed that in the second lecture. For example, here if you have one battery with, let's say, 12 volt, and if you have another battery with 6 volts, and if that's connected in parallel like this, this circuit cannot exit at all, because if you apply KVL around this loop, results in 12 volts plus 6 volt is equals to 0. Minus 6 volts is equals to 0, which is not valid, right? Which is not equal to 0. So that is why this source transformation, whenever you are doing this kind of problem, make sure you are only adding voltages if the voltage resistors are in series, and only adding the current source if they are in parallel. That's all. With that, assignment 3 is out and is due next Thursday. I'll see you tomorrow in the class. Thank you.